Good evening, everybody, and welcome to our presentation this evening. The presentation will cover various aspects of modular construction, how support and stability are provided, some challenges in the George Street and College Road projects. We'll look at temporary work solutions and why they were required, some modular connections and principles, structural models and modular layouts. We'll briefly look at fire and finish with embodied carbon. Then Shane will look at modular engineering from the point of view of the engineer providing traditional building elements. This is a typical volumetric module. It's an off-site element. It's factory constructed. The structure of the building is included in the module, floor and the ceiling. The floor in this module is a concrete floor. Ceiling is lightweight steel. Internal walls can be included. Bathrooms can be finished. Rooms can be decorated, and depending on the use of the building, it can possibly be furnished. For MJH structural engineers, the work starts in the design office with modularization. We do engineering design. We do module drawings and details. Our information is passed to the modular factory where walls are fabricated, services are added to the walls, boarding is added. The units are assembled into 3 dimensions, finished out. And at the same time as this work is going on, excavation will commence on site. Foundations will be constructed, superstructure, transfer slab and a concrete core generally. Once the podium slab and the concrete core are in place, modules are taken from the factory, put on trucks, driven to site, picked up by tower crane, placed on the podium slab around the core. Here you see one of the projects in progress. Up near the top of the building, we have the modules. The last few modules are dropped in place. Cladding is commenced and is close to completion. The parts near the bottom of the building, we have mast climbers on the elevations. And College Road, this is the completed building. We'll be discussing design and engineering issues related to the Vision Modular System, which has been used to deliver buildings ranging from 2-story to 50-story. This diagram may help to explain the structural system. The center of each. Sorry, I'll just turn the camera there. The modules all include structural columns that bring the vertical loads down to the transfer level. The modules have concrete floors that are interconnected, so all horizontal loads are transferred to the core. We use different types of modules. We have corner supported modules where the structure of the building is minimal, where there's a number of columns around the perimeter spaced quite a distance apart. And we use wall supported modules where there are more structural members distributed throughout the walls. For supporting those modules, when we have point loads, we require to pick up those areas. When you have wall supported modules, you have to have linear supports for the wall elements. In general, we use podium slabs, which works as a solution for both types. The module manufacturer will look at limitations related to the system. So they will have factory limitations, the size of module that can be manufactured and lifted in the factory, what fits through the door, what fits through the factory. And then national roads will have allowable loadings, bridges will have limits on the heights. And then when you get in close to a project, you may have local limits that apply, bridge heights, road limitations, and cranage limits on the actual site. The process of modularization is where we break up the floor plans into a workable layout to maximize the offsite solution in the most efficient manner that we can achieve. So we try to minimize the number of modules. We try to minimize variations in the module types. We try to maximize the coverage. This process is quite detailed and is taken together with the modular manufacturer and the architect. We use a number of different shapes of modules. The majority of buildings are done with mostly rectangular modules. Some of the other shapes you see there are quite commonly used, sloped end and tapered end particularly. Vision Modular System is very flexible, and all the shapes you see here have been manufactured at some point to allow us to do various schemes. The concrete transfer slab provides a versatile solution allowing modular layouts that are completely independent of the structural grid below. This is the most common solution for medium to high-rise modular construction. The concrete slab is good for fire. It's flexible for layouts. It provides quite a stiff structure for loads. It has an ability to handle secondary issues and is good as a working platform. Transfer slabs may range from about 600 deep for 6 stories to maybe 2 meters deep for 40 stories. These depths are very much related to the size and spacing of columns, and Shane will discuss this further. From a practical point of view, it's best to construct the transfer slab to standard tolerances, and then the modular supplier has a leveling zone to achieve whatever accuracy they require. It is also possible to use steel transfers, but additional care needs to be taken. Steel is a lightweight solution and may easily be placed in stages. It's also an offsite solution, so is very useful when you're doing modular construction. In terms of design or detailing, the deflections need to be carefully considered. The loads may not be centered on beams, so the beam outstands may need to be stiffened. There may be unbalanced loadings on both sides of a given beam, either during the placing or in the final configuration. The addition of fire protection to the steel structure is another operation, and the underside of the lowest level of modules are more exposed than with a concrete transfer slab. When modules are placed on the supporting structure, the structure deflects and various forces arise in members and connections. As each level of modules are placed, the deflections increase. Finished and often decorated modules are placed, and if these movements cause stresses, then damages may occur to the finishes. In extreme cases, there could be preloading of the connections, so a staged analysis might be informative in this case. We use concrete cores for stability. For medium to high-rise modular construction, they're a most effective solution to provide a very stiff, stabilizing element, and is a very traditional form of construction, is very well understood. The only difficulty with using concrete cores is that they need to be finished before module placing commences. This is our project at College Road. The building has traditional construction on the lower floors with exposed perimeter columns and a double height space, all facilitated by a deep transfer slab above. The residential levels above have layouts that are structurally independent of the lower levels, thanks to the transfer slab. And at the top of the building, one tower extends higher than the other. In terms of location, both the 101 George Street project and the College Road projects are located in Croydon. That's George Street in the center of the video clip there, with the College Road site appearing behind it. And the upper image here shows the modular layout that we use on that project. There are a couple of rectangular modules internally, but all the perimeter modules have shaped ends. There are two towers, approximately 20 by 16 and 35 by 20, with RC cores 7 by 7 and 10 by 10 centrally placed in both towers. Similar to the George Street project that we did, the College Road project has two towers of different heights. The towers are 35 and 50 stories, providing 817 co-living homes and 120 affordable, using about 1,725 modules and built in a 32-month construction program. Our early scheme analysis for George Street identified quite high tying forces between the towers at the upper levels related to the height differential. This informs some of the planning constraints early on in the project. We refer to this as the top two floor tying issue. With College Road, the alignment of the towers meant that the George Street solution that we had previously wouldn't work. So the options are at an early stage to separate the two towers, which obviously simplifies the module design quite considerably. It adds other complexities, such as fireproofing, cladding issues in the gap, wind tunneling between the two buildings, potentially planning problems. If you separate them too much, the buildings won't fit on the site. The cores would also need to be larger because they rely on each other for some stiffness. The alternative was to tie the towers together, which adds the complexity back into the module design, but it removes all the other issues. So the cores are combined for stiffness and removes the gap issues between the buildings. This is the solution that was chosen. When the buildings are complete, we have these higher forces in the top couple of floors. If we tie the towers as we construct, we have high forces at each new top level. So this is a transient tying issue. This would be a very inefficient solution, as each connection is designed for high temporary forces rather than the much lower permanent forces. If we build the two towers full height and then connect them, we have a variation of this transient force. We undertook wind tunnel testing for the current building layout in the surrounding area. We also assessed with future planning in mind. see what effect the new buildings would have on our development. And in addition, we undertook temporary stage wind tunnel modeling with some modules in place to assess the tying issues and forces during the construction phase of the work. Early on in the project, you have two tall, slender cores. The H/D ratio is quite high. There are independent cores exposed to wind loading during the construction phase. They have different stiffness, so the cores may not match each other, and they may move together or apart during high winds. When we add in the modules and connect them between the two cores, we effectively tie the cores together. So then you end up designing for the short-term construction wind rather than the completed building forces, which can be uneconomical. The solution we adopted was to add 3 levels of temporary tying over the height of the building. This reduces the forces in the short term. So when you drop the modules in, the forces drop quite significantly. And then your connections are designed predominantly for the permanent loads in the building. This is an image of 101 George Street and the temporary tying which went between the corners of the two cores. These are part plans. You can see the little blue dots in each of the modules. This is the point where the module hangs from the crane. So pretty much every module can be placed on the building by dropping it to a certain height and bringing it in underneath the ties. When we came to College Road, because the two cores aligned and the ties were on the corners, the yellow dots show the modules that couldn't be fitted once the temporary tying was in place. So we had to consider a different method of tying. We placed Tower A up to the level of Tower B. And then we placed Tower B full height. And then once that was in place, we tied the tops of the two towers, the cores together above the top of the two towers. And then the connections were fitted from the bottom up. And this reduced the temporary forces in the building. We undertook various analysis to inform the design and the temporary tying, and also to understand the forces in the permanent connections. Many scenarios were considered in order to achieve the most efficient solution in terms of work, materials, and maintaining a rate of placing of modules. We undertook similar analysis for the George Street project. And here you can see the temporary ties in George Street at the 3 levels. The floor of a modular building is made up of a number of discrete slabs that are tied together with connections. They are tied together to form a structural diaphragm. We undertake computer modeling that allows the forces to be assessed for all the load conditions. If we take a very simple analogy and look at a point load on the corner, it generates forces between the modules, tensions and compressions, and some shears. If the force is large enough, those forces transfer back into the core through the connections. Larger again, and those forces transfer to the other side. If the forces are large enough to displace the core, then they result in forces between the two towers. So you can imagine the connections are quite important to us. So when we think about connections for modules, we try to create drop-in-place connections where possible. Simplify the work on site, minimize the work on site during placing. You minimize wet trades. If there's complexity, you try and keep it in the factory and keep the simplicity on site. And then you try to keep your connections out of areas of high finishes like bathrooms and kitchens. If we take, for example, something very simple, like we want to connect 2 bars together, we might use a tie plate. And the 2 bars will have some level of tolerance on them. In this case, they're shown close together. They're not central on the opes. So we might use an annular ring, which we rotate into place, fills the gap. If the 2 bars are further apart, you can just rotate the annular ring and it also fills the gap. So that's a solution that allows us to provide a stiff connection between two bars. However, if there's any vibration in the building, that circle can rotate. So therefore, those 2 faraway bars can start to move closer together. A better solution in this instance would be to use the top right-hand corner. You can see the hexagonal shapes. So if there's any vibration in this instance, they can't rotate. The hexagon could be an octagon or could have more sides depending on the potential force. The circle provides you with linear tolerance, whereas the hexagon or another shape like it provides you with stepped tolerance. So some thought has to be given to what accuracy you can achieve and what level of tolerance you desire. These are some images of our engineering models in ETABS. On the left is a staged model with the temporary ties between the towers. You can see each level of modules being placed. And as they reach the temporary ties in the computer model, the tie is removed to see the effects. This model allows us to look at various things like the cores of the ties, single modules, one tower in place, or the full building. We break up the building into the modules. Each module is then looked at for engineering design. So you look at the lifting, because you lift in the factory and you lift on site. And you also look at placing, when you put the module in place and when it's occupied. All these generate different forces, shears, and every instance has to be looked at. There's also transportation to get the modules to site. With manufacturing offsite, the material densities and quantities are very well understood, and building weights can be assessed very accurately. Of course, the modules can also be weighed on a couple of occasions. We pick them up in the factory, so the module can be weighed, and we pick them up again on site. So you can assess the weight of the building very, very accurately. The support structure for a module is best placed in the corners and pushed out to the outer edge so it picks up the structural members. As the structural members reduce up through the buildings, they are also pushed to the outer corner. So there is an eccentricity generated and must be considered in the design. We use our own range of column sizes rolled specially for the vision system. The steps and sizes are the most efficient that we can achieve. In George Street, there was over 7,000 columns in the project, and each one is designed individually for the specific location in the building. With modular construction, because you manufacture elements offsite and then have to fit them together, you have to consider your tolerances. It's possible to make things very accurately, but not possible to make them highly accurately all the time. So it's best to understand the level of accuracy you're achieving and engineer your project to suit. If you have a reducing or increasing gap between modules, at some point that can become a significant problem where modules don't fit. The same issue occurs with traditional construction. If the traditional construction is out of tolerance, that can cause significant problems. So accuracy of the traditional is very important. In the manufacture, you have to figure out what level of tolerance is acceptable. There's lots of things to consider in terms of cost and accuracy. Very briefly look at one or two projects. Mapleton Crescent. We had a river on one side, we had a road, and we had an electricity substation. The site area was quite small, 476 square meters, and we were placing a 27-story building on the site. This is the plan layout with an off-center core. And then we had a number of rectangular modules that were fitted around the core. But as we came in close to the internal corner, you can see the shape of the modules changes. And again, there are a few rectangular ones. And then after that, they're all forming a little jigsaw. So being able to achieve different shapes unlocks certain sites to a modular solution. Site wouldn't have been possible with just rectangular modules. Also, the site had been set there for a long time because traditional construction was too expensive to develop. The site was just too difficult. And the completed building, which has won a number of awards due to a high level of finish. Apex House in Wembley. It was 2 low wings and a tall tower with a concrete core with 28 levels of modules on that one. What's interesting is on a given floor plate, only 40% of the modules are rectangular again. All the other ones had some shape changes. This allows flexibility for the architect in developing the project. This is one of the final modules arriving to the Apex project in Wembley. The module is lifted by crane to the top of the building. So larger modules reduce the number of lifts and therefore overall time on the hook. Placing the module is a fairly simple operation undertaken by a small specialized team. Modular construction has a significant effect on site workers. On the top of the building, you have a small crew of highly trained workers doing very repetitive operations. The working area is very tidy and very safe. Once you come below that level, Every worker works in the same conditions, whether it's on the ground floor or the 50th floor. They're all internal in a weather-controlled environment, which is the same on the first and last levels of the buildings. Even the workers on the traditional levels, because the majority of the building is done through modules, the traditional elements come off the critical path in a lot of cases, and so the work is not under as much pressure. A full tower fire test was undertaken on the system. 6 modules were placed together, loaded, and instrumented for movement and temperature. The module on the bottom in the center was loaded out with timber and burned. Here you can see the fire in the lower module. The adjacent modules were perfect afterwards, with no heat or smoke damage, and these modules were used in the final building. The fire-tested module, which is the one to the left of this, had damages to the finishes, but the protection to the structure remained in place. The modular detailing is completed in Tekla, which allows for very detailed 3-dimensional models. This improves coordination throughout the team, helps to control costs, minimizes the material usage, and helps reduce waste. The improved coordination reduces risks of mistakes. We undertake collision detection, and communication of the details is very simple using this system. A number of studies have been carried out on the system and improvements over some traditional construction methods established. The reduction in waste and increased recycling are easy to understand when the work is factory-based. Combining many parts of a building into large deliverable elements results in dramatic changes to construction logistics. Then the dual nature of the construction with the site and factory happening at the same time helps reduce the building completion time. The studies indicate the system has reached a 2025 target, with some buildings already achieving the 2030 targets. Vision have put a lot of money into R&D and will continue to improve the system with the aim of staying ahead of targets and ensuring the system remains at the forefront of construction. I'll pass you over to Shane now, and he will take you through the remainder of our presentation. Thanks for your attention.
Yeah, sorry. So it's just worth noting that funders and insurance, providers that would generally want, they generally want a single point of responsibility for the overall structure design of these type tall buildings. So the main consultants, their PI and collateral warranties need to cover the overall building, including the modular design. So you really need to have a good understanding of the impacts of the modules on high-rise building design. So as Michael briefly alluded to, what would be in your scope of design is, design the foundations, your ground floor slabs, transfer slabs, and your RCs and your RC stability cores. You can go on to the next slide. And then modules stack around the cores to complete the building. So what we begin to do is we get from Michael or the architect and modular supplier a general floor plan with module column positions, and we would build an independent final element model from the one that Michael would have been talking about in DTABS. And you can see this screenshot on the left hand side is 101 is College Road, and you can see there the thicker in blue, the thicker modular floor slabs we would have had at the step in the buildings for the permanent high level forces. But as Michael discussed, with just the temporary forces, the rest of the modular slabs worked at the thinner 150 mil thick slabs once we tied the cores in the temporary case. On to the next slide. So the big fundamental difference between tall modular buildings and tall traditional buildings is the requirement for a sliding joint between the RC core and the modules. And the reason for that is that in a traditional, say, mixed steel frame building or steel concrete core building that you see around the City of London, generally you'll have an RC core, and then say 6-7 meters away you'd have a steel external steel frame, which have axial shortening issues like the modules do as well. So if you go to the next slide, you can just see in a traditional building your external steel columns would shorten as the building is erected. Next. But then that's generally, you can overcome those issues with, floor level compensation by casting the floors at a slant upwards, so that in the final situation you have a level floor. But because of articulation and the distance, between the external column and the core wall, your connection forces and your cast-in plates or connections to the core wall are not that excessive in general. But in a modular building, the gap between the steel column of the modules and the wall itself is only about 50 millimeters or less. So you go to the next. So as each module is erected, because the core is in place first, they elastically shorten. And if you have a rigid connection to the core, that's just going to shear off due to the shortening forces, which will be massive. It's effectively going to try and prop the building off the core, which you want to avoid. And then you have long-term continuous movement of the core, because steel will instantly elastically shorten as the modules go in, but the concrete core will continue to shrink downwards due to shrinkage of concrete and creep. So you have to allow for that movement, and you don't want the load or weight of the core being transferred into the modular units. So in the FE model, those movement connections need to be picked up, so you can calculate the correct forces in the core walls. So the plates themselves, sorry, just go back to the previous slide for a second. Yeah, so the plates themselves, you can see, are quite large. That the picture on the right hand side is of George Street, I think. So the cast-in plates, they need to be quite big on area, to give you your tolerance for a few issues. So you've got your insulation tolerance on site via the slip form, then you have your tolerance for the module installation, but then you also need tolerance for the fact when the bracket itself is installed, that you have to have enough vertical travel distance to allow for your movements, both short-term during module installation and long-term movement of the core. And there's a series of calculations that we would go through with MGH in calculating, the connections, say down at level 10, are installed in the core, which could be 3 or 4 months before the modules are there. So they're going to shrink. They're going to be in a different position on site relative to when the actual module is installed. And that times stepped analysis needs to be done via the FE models to establish the accurate installation levels of every plate. So when you're looking at low pats, they are a bit different than a traditional building. So you can see on the right-hand side there that the module vertical loads go straight down the modular posts, down to the transfer level. And inside your core, you've only got the self-weight of the core. So the dead weight of the building is not applied to the main stability element until below transfer level, where you can see the green and blue arrows joining together at the base. From a lateral load point of view, then the horizontal load is applied to the core, and you get a push-pull effect on the core, which obviously gives you high tensile loads on the windward face. And in a traditional building, you'd have some significant floor loads at that level, but in a modular building, you've only got the weight of the core, so we do get some significant cracking and deflections in the core due to that issue, which tends that you need slightly heavier, bigger cores than you would for a full traditional building. In terms of core positions, like most other tall buildings, we always really try and get the core into the middle of the building. They typically have between 400 to 600 mil thick external walls. Like in College Road at 50 stories, we had 600 mil thick, but generally you'd be talking in the region of 400 to 500 mil external walls. And a lot of that reason is to give us some mass due to the lack of floor loads in the core. So with the Vision system, we do use concrete cores, as Michael alluded to. We find in the UK market, they're quick to construct. Slip formers, you can do a floor per day. There's a lot of available workforce to do that, and you get inherent fire acoustic performance. And as briefly discussed a little bit later on, they have good damping effects as well in terms of wind accelerations compared to a pure steel buildings. But steel frame cores and our steel shear plate walls are possible. They're done internationally in the American markets and in Middle East. But it's not something we've looked at in much detail with the Vision system in the UK. And just in red at the bottom of that slide, so our fundamental design kind of philosophy is that we don't rely on the modular floor slab for any outer plane lateral buckling of the shear walls. So we need the cores to be fully, all walls, like locally and globally, to be fully their full buckling capacity without relying on any lateral restraint from the modules. So in an eccentric core, not ideal. If you go to the next slide, the reason is that unlike a traditional building where you've got a good solid slab, the modules have individual small connections, which would be obviously the philosophy in modular is you want to minimize the number of connections and the types. So if you have a long cantilever, you get fairly significant forces in the both in the modular to modular connections and into the core itself. And then we also get issues with vibration, getting torsional first modes of vibration and increased cracking, increased tensile forces in the cores. We have a few options open to us on how we alleviate that issue. So one option is we install a shear wall on one end. Now that's quite good because it can fit, in between apartment layout, in between apartment party walls or walls in the apartments. Doesn't have too much of an architectural impact, but we still have the same issue that we do with the cores, and that the module, the amount of floor area of the module applied to these frames is very small. So as you go, once you go above 15 stories, the tensile loads in them get quite big, and we can't generate the mass of the building to hold those frames down. And as well, when they're mixed with a concrete core, the stiffness of because you're mixing materials, the stiffness of the concrete core is significantly higher than the steel frames in general. And sometimes they don't generally reduce the connection forces to the core as much as we would like, due to the high level of stiffness of the core versus small steel frames. So one option A is we add another core. That's great for the overall structural design. We go on to the next slide then, but then you get that tie force between the modules, between the two cores, which the modules have to transfer. That's unavoidable, complicates the modular design, or we have to brace the cores together. Not exactly ideal either, but is possible. And then so if we were looking at a building from the very beginning, we'd really be pushing everyone, the architects and clients, to try and get a single core option to work as a starting point, because it simplifies all your modular connections. We can elongate the core like we've shown there, to reduce the cantilever effect on one side. But there is obviously drawbacks in terms, especially with new building regs and the number of stairs and fire escape routes that obviously need to be considered as well. But from a structural perspective, a central single core is the best option to simplify the modular unit design. So to get over the cracking issues then that I discussed previously, we've done a few options. Like at College Road, we increased the level of the transfer slab. Now, that obviously sacrificed some apartments that may need to be fitted out on site, or what we do a lot of time is move amenity from the roof down to the lower levels, put them into the additional areas. And when we push up the transfer slab, it keeps the lower part of the core in compression, reduces cracking and stiffens it up. And it also gives us the opportunity to put in more shear walls, to fully really stiffen the base of the building to compensate for the increased deflections above transfer level. You could increase the self weight of the core, thicker walls, thicker Landon slabs. Can be an easy fix, but it's not, sustainability wise, and the weight of concrete and cost of materials may not be ideal in all situations. And one other option is, external outrigger walls or frames, which again is a traditional building option, or a very common traditional building option. But we're back into the same kind of situation where the external outrigger columns, you then need to rely on the modules to prevent out-of-plane buckling, which, if you're using a lightweight modular system, or it's not something that we're that comfortable with, relying on modules for global stability for buildings of this height. So there's one interesting project which is still under design development. It's not built yet, but this is a 30 Marsh wall in Canary Wharf. It's 50 stories high, over 3 stories of basement. But if you can just see, I can't use my mouse, but the bottom of the core there, you can see there's a T-shaped. So the original scheme for this, when we looked at it, was we had the 2 apartments to the left and right of this, as part of the RC frame. So the core walls were on the left-hand side and right-hand side of those apartments to give us, that was the amount of stiffness we needed for the core to work for deflection and accelerations. But due to deliveries, and there was a few issues with actually the rate of rise, it wasn't actually possible to slip form a core that big with the travel restrictions and lorry restrictions in Canary Wharf. So our client requested that it wasn't feasible to build this job unless that core was reduced. So what we did was we induced a T-shaped kind of hammerhead core wall, as shown there. So we go on to the next slide. So in a normal building, that's relatively straightforward because you can rely on, again, out-of-plane buckling of that T. So that T takes quite a big wind load or quite a large compression load when wind blows from the north to the south direction. And you could normally just rely on your concrete slab to resist that out-of-plane buckling with just compression stresses or axial stresses into slabs back into the main core. And on to the next. But we don't want those forces going into the modules because the modules have, isolated connections. You're going to rely on, a single module connection for potentially propping the building up and preventing global buckling of the core. So our solution was that we decoupled the modules from the core wall, and we had a sleeve cast through the core walls, or proposed a sleeve cast through the core walls, which allowed continuation of your module diaphragm, but decoupled the core wall from the modules, ensuring any out-of-plane buckling forces were not propped by the modules, or any differential movement in the core was completely separated from the modules. And then to justify that, we did a full buckling analysis check on it. So we did a full scale buckling shape. Then we did a nonlinear imperfection analysis, and then use that then to do a second order analysis to calculate the horizontal reinforcement needed in that hammerhead to take the horizontal buckling forces within the wall itself and not rely and allow it to move horizontally, which we needed this in any case for it to be stable in its freestanding state as a slip form, but then it was also part of the permanent work solution as well. Very briefly, just the parapets. So in general, the modules, by the time the modules reach the roof level, the posts are going to be quite small to make them efficient, potentially 150 by 150 or 175 by 175. The connections and the modules posts themselves have very limited moment capacity. And in general, the tall buildings have quite high M&E plant, and planning conditions normally require, you could have 7-8 meter high parapets, and it's generally just a point to note, it's not possible to cantilever a parapet that high at that height off a module. So generally, we do need to allow for bracing back to the cores, which sometimes is a client or planning issue, but it's something that just should be considered at an early stage. The transfer slab, as Michael said, so we found is by far the best option to control, deflections and flexibility. It gives you a good level soffit, and it allows good flexibility in the column layouts. Generally, what we find for these very tall buildings, if you're at a 6 meter grid or so of columns, that punch and shear is the main driver. It's not deflections, generally not bending moments in the slabs. It's pure punch and shear. And when you've got a slab 2 meters thick, your punch and shear perimeters at 2.5 D from the column faces overlap, so you end up pretty much with a full flat slab in most cases anyway. Next, yes, this is just a slide of a portion of the transfer slab at College Road. So you can see there from the kind of red dimensions, they're all the vertical rising openings in the modules. So you can see there's quite a dense array of openings, because each individual module has its own riser, so that all services vertically stack. So every module has an SVP, or every apartment has an SVP, every kitchen, and they all vertically stack throughout the building. So there needs to be early stage coordination of the position of those openings in the modules and how it works with the below ground layouts. Because the columns, we need to avoid punch and shear issues with the columns, and the whole layout needs to work together. And that's all very early stage decisions. So the architect and client needs to understand that it's not just setting the module layout, it does have an impact on the lower levels as well. The final point on the transfer slab then, another kind of contentious issue with architects is on these tall buildings, there's quite high compression loads in the external module posts. And in Eurocode, there's quite a significant reduction in your allowable bearing stress near the edge of the slab, due to the picture on the right hand side there from Eurocode 2. So it's almost always the transfer slab needs to be at least a minimum 200 mil thick, or 200 mil beyond the bearing plate of your module, to give construction tolerance and allow the bearing stresses to be actually feasible. And it generally squeezes your facade zone just locally at the transfer slab level relative to your typical module slab zone. So some special consideration for installation and cladding finish is needed. The foundations, that's just a slide I put in. They're pretty much going to be very similar to a traditional construction option. By the time you go below transfer level, your load paths are very similar. Your forces should be generally quite similar, especially if using modules with concrete floor slabs. They're relatively similar in weight to what you would in a traditional structure. Obviously, if you use a lighter weight system, there's options for saving on your pile cap thicknesses, pile lengths, but there's some drawbacks in terms of the dynamic performance of a lighter system, as I'll discuss in a minute. So on both all recent tall buildings since 2016, we've been undertaking wind tunnel testing, even for buildings up to 20 stories high, because there's uncertainties in terms of how these would perform, especially with funders and people in general. There's a perception that modular buildings are much lighter and more flexible, and there may be issues with motion sickness or people feeling motions at the top of the buildings due to wind. So what we would need to do as the main consultant is model the full building, import all the modular structure as best we can at the stage of design. And the wind tunnel consultant then needs structural properties of these buildings. Now, Eurocode has some guidance on kind of standard input parameters, especially for damping. There's a copy in the table in the top right-hand corner there for steel concrete or mixed concrete buildings. But those values for modular were not very well defined, especially when we started looking at the likes of 101 George Street 3 or 4 years ago. There was the damping levels. There was no database for us to work from. So we were quite conservative for 101 George Street. We assumed all the modules fully pinned. They had no stiffness, all stiffness into the core. That's what we'd always do at ultimate limit state. But at service limit state, which is what accelerations are, the modules do have some stiffness, but we conservatively ignored it for the initial design, and we took a relatively low damping value of 1%. The lower end of a mixed steel concrete building in Eurocode. So natural frequency, so the main parameters that the wind consultant needs is natural frequency, mode shapes, and masses of your building. So any building, it has its own natural frequency, which is just a function of its stiffness and mass, and it's how a building will vibrate with no external loads. You click the next slide there. Yeah. So we've very good understanding of certain elements of the natural frequency calculation, which is directly proportional to mass and stiffness. So we know the mass of the RC core pretty accurately. We know the stiffness of the RC core because it's concrete, and we know the mass of the modules because they're very accurately in a factory-made product. However, on to the next, we have a very low degree of certainty of, especially the damping for high-rise modular buildings, which has a fairly big impact on the final acceleration output in the design. And also the stiffness of the module units themselves at service limit state is questionable. And we were potentially, too conservative by assuming they contribute no stiffness, considering they have a lot of internal steel columns, steel walls, internal partitions, fully sealed units at 3.5 meter center. So there is significant internal structure that we generally ignore at ULS state, but needs to be considered or can be considered at service limit state. So on George Street, because of our initial low assumptions on the module stiffness and damping, we did design a mass-tuned liquid damper with a company called BMT, who were in business at the time. So that was designed in based on our initial assumptions, and we had a position for it at the top of the core. We go on to the next slide. But we couldn't finalize the design because even the design of the mass-tuned damping tank depends on the actual frequency of the building and the actual stiffness, which we couldn't really confirm with certainty at the time. So we started, which is still ongoing, a research project with the engineering department in Trinity College in Dublin. So we installed monitors on top of both freestanding cores and also on the completed buildings for both College Road, for both George Street and College Road. So our hypothesis was that because you've got a lot of connections and you've got the vertical movement joint between the core and the modules, that this allows for a certain amount of energy dissipation, which may not happen in traditional buildings. And also the aim was to establish what kind of stiffness do the modules actually have with all their internals, kind of non-load bearing steelwork, but it's still relatively stiff steelwork internally in the vision system. And they have the concrete floor slabs as well, which is quite a high in-plane stiffness. So we modded, just back to the Yeah, so that the bottom of the thing there, yeah. So we monitored the accelerations, and yeah, it was really just to establish the true frequencies and the damping values, both during construction and towards the end and for the completed building. And that's just a picture of, so the acceleration monitors now, they're just a mobile phone. The technology of the mobile phone is good enough now to monitor acceleration. So that's all it is. And we placed them like on the cores, and in College Road, we placed one on the far left-hand side as well, just to monitor for any torsion that affects on the core as well. So research find, now this is still ongoing and will be ongoing for a few more years, because we need to build up a database of all these buildings and exactly how they perform. But the natural frequency of the freestanding cores, which are the slip formed freestanding cores, were within 10% of what the FE software says are predicted. That was assumed to be the case, because concrete is fairly well understood, and we fairly good accurate inputs from Eurocode to check that. But counter to what we expected, the natural frequency of the completed modular structure was actually significantly higher than we had assumed. So as the mass of the modules was added to the building, our FE models would have assumed conservatively that the stiffness didn't increase, because the modules were pinned, and the core was the only stiffness. But as your mass went up, the frequency should go down. But that wasn't the case. The frequency remained quite consistent as the modules went in, and the vision modules at least do provide significant stiffness at SLS state. Now, it's not something we consider at ULS, but at SLS they do. So however, the damping ratio was actually within what Eurocode recommended for mixed steel concrete buildings, between 1 and 1.3% for George Street. And that's quite close to the 1.27% recommended in Eurocode. So that's where we are with that. But obviously, we're going to be continuing to monitor the buildings going forward. But at 101 George Street, we ended up not needing the liquid tune damping tank, because the frequencies were significantly high enough to not need the tank. And we were, even with the very conservative assumptions, we were right on the borderline with the accelerations anyway. So that was a good result, that we were able to remove that and prove the system works. Just in red text at the bottom, there's just a quite important note that all this research is purely for the vision system. It's obviously other systems with lighter floors or different internal bracing arrangements wouldn't be applicable to it necessarily. So it is purely for the vision system, but it's still interesting nonetheless. And I'm just going to finish on the cranes, which I think is always interesting. It's probably more of a contractor problem than the consultant engineer, but it does need to be considered, especially for the design of the cores and their connections and the forces from them. So in a traditional high-rise building, as you see around London, once you go above, say, 25 stories, you generally need to tie in your crane to the building. So to build the cores, we would put in an external crane, which is tied to the core in a traditional manner, which would build both cores, which you can see in the middle photograph there. But then the ties block the installation of the modules, because they need to be dropped straight down. So they need to be removed to actually install the modules. So the solution that we've always used is that cranes are installed on top of the core, which gives you a full free zone to install all the modules. And they can be quite heavy with the concrete slab system. They can weigh up to 30 ton. So they're quite big luffing cranes are required, which require fairly significant steelwork and post-tensioned cast in high tensile bars into the core. Always needs to be designed and coordinated, and those tie-in bars need to be coordinated with the module connections and various other items as well to make sure the whole thing works. That all needs to be done at an early stage. But then the challenge is removing the crane from on top of the core after the building, because we generally can't rebuild the middle crane because it's probably blocked by modules. Or we've looked at tying to the modules is very difficult as well, with the tie forces. They're very big for the module connections. This is very quick. This is just the crane strategy for College Road. So we'd crane in the middle, built the core, and then the crane on top of the cores built the modules. And then, as you can see in the slide, on the very far right-hand side, to take off the taller one, the crane and the smaller one was built up and tied into the very top of the core so we could tie into the concrete. But we were still left with the challenge of taking down the crane on the left-hand side. So for the first time, we installed what's called a derrick crane on top of the modules to remove the the remaining tower crane. That had a few challenges in that, the forces were still up to 300-400 kilonewtons per leg in this crane, and it was sitting on module posts 40 stories high. So there was quite significant, axial compression or axial shortening, which was significantly overloading the module posts, the local module connections. So we came up with a grillage design, that's actually 4 modules. So it was designed to exactly evenly distribute all the crane loads over 4 modules. And everywhere where there was a 2 module post tied together, it was an even load, so it didn't locally overload the connections. And that crane dismantled that crane, and then it was taken down by hand almost, and on top of the building afterwards, the smaller crane. So that concludes my section of the talk. Apologies for the awkward start there with the sharing. I'd just like to take the opportunity to thank Vision Modular Systems and Tide Construction for the opportunity to work on these great projects. Led from the front by their CEO, John Fleming, Vision have invested significant finance and resources into the research and development of this system, which has allowed us to reach these heights, as you can see from the sample of buildings that we've done in London recently. And John and Vision, structural engineering is very high up their priorities, which is great to see for a client. And we're very grateful, both us at BMC and MGH, for their trust they've placed in us to design these buildings and help them develop the system going forward. So thank you very much, and I'd like to hand back to the chair.
Wow, that's fantastic. That's generated a huge amount of interesting questions. And the first one, for either of you, if you'd like to say which one of you will take the questions, just what are the flaws in the modules and how are they connected together to form a diaphragm?
Sure. So the floors of the modules are concrete slabs, generally 150 mil thick, and each module comes out of the factory with its own floor, fully solid concrete. And then when we place them on site, there are a number of discrete connections at various points along the side of a module to interconnect them. And similarly, there's points on the modules where we connect back to the core.
Okay, great. And those connections, they're steel plates, Michael, is that correct from your slides?
Yes, they're significant steel plates, and some of them are 25 mil thick. So they can take very high forces, much higher than the forces in the building.
And are they welded on site on your system?
Yes, the majority of connections we do are welded. When we place modules, we have a bolted connection internally in the columns to connect them through the full height of the building. But then connections that are not under time constraints, where we're connecting module to module or module to core, those ones are welded.
Okay, great, thank you. And then I think this one is going to be for Shane. Shane, could you just talk about the transfer slabs? Are there any significant differences in the design of the transfer slabs? And also there's a question of why the cores have to be completed before the modules are placed. Okay,
well, starting on the transfer slab, yeah, like I said, the probably main unusual difference is that the bearing stresses under the modules, because especially the way Vision designed their modular posts, they're very, very efficient. And to stay inside the apartment layouts, generally, rather than going, say to a 250 by 250 or 300 box section, the wall thickness is increased, could be up to 25 mil thick. So if you imagine when you come to the transfer slab level, you've got like a column with 25 mil thick wall, but the actual bearing area, the bearing stresses under it are very high. And that potentially drives the grade of concrete that we need. Is actually local bearing under the columns is what drives the grade of concrete. And then it is punch and shear. Then it's really trying to get those openings, or many openings in the modules, away from the columns, because punch and shear can be a challenge. And in terms of the core, the reason the core needs to be completed, well, if it's slip form, the actual slip form platform itself obstructs the module install. And it's, most high-rise buildings, the crane, like I explained, needs to go on top of the core, unless you have an external crane. Yeah, potentially, if you have an external crane that can be built on its own base, capable of installing the modules, it is possible. But usually, commercially, there's only one crane put up to build the cores and there isn't the crane time to install modules and build the core at the same time if using slip form.
And Shane, do you have to design for more stringent deflection criteria on the transfer slabs, or are they normal criteria?
They're a bit more stringent. Yeah, we try and aim for a span over, say, 360 between any two module posts for total load rather than just span over 250. Yeah, because that's for long-term deflection as well. But yeah, it can become an issue if in some of the lower-rise buildings you might have 9 meter spans, but in the high-rise buildings, it is the punches here. The deflections generally aren't too much of a problem at 2 meters thick with a 6 meter grid. But yeah, but they are a bit more stringent.
Great. We have a question here that I was going to ask. How you tackle progressive collapse generally in modular construction, but also on such a high-rise tower?
I suppose, yeah. Well, the buildings have full vertical and horizontal ties first. That's the primary solution. But in addition to that, we also look at notional removal of columns. So we've done finite element modeling and some testing to show that you can remove columns and modules can still stay in place. And together with the vertical and horizontal tying, I think it's probably pretty safe.
That was a question that came up later, which we'll go to. How do you tie the columns together? Are they corner columns that you tie together, particularly with sort of restrictions on access?
Yeah, so like I suppose there's various ways you can tie your buildings together. We in the corner post system, we have a vertical tie that runs down through the center of the columns. That's connected from the top of the column. So you always have access to the four tops of the 4 columns, and so you can make that connection. And then horizontally, some of the ties are a lot of ties are in the corridors, and some of them might be on occasion in the rooms. And we have also got horizontal connections on the perimeter of the building. By moving the connections onto the perimeter of the building, it means you can finish out rooms.
There's some fascinating IP in there. Moving on to the fire test, which was very impressive. Can you recall what the standard of that, what standard you did that to? That obviously that's sort of on everyone's minds at the moment.
There was two fire tests done, but I know they were done to a full 2-hour ISO fire test.
And just if I can broaden that, Michael, I know from my sort of experience that how did you generate some of the design sort of solutions and analysis, because this isn't a well codified area, isn't it? You really have done some ground bearing work on, or a lot of ground bearing work on this.
I suppose we've been at it for a long time, Patrick, to be fair. So I personally have been involved in very little else for a number of years. So I've given a lot of thought to a lot of things in this. I think that helps certainly when you're trying to progress and develop, that your thoughts are all about one thing and one system. And we've developed slowly. We started out with 6-story, then 11 stories, then 25, 30, then 45. So like it was a progressive increase in height of building in developing the technology. And as Shane mentioned, John Fleming of Vision and Tide has pumped a lot of money into research and development. We've had numerous people involved to help us out and guide us. We started out with talking to people in Hong Kong about high-rise. We had the Steel Construction Institute. We've gone to a number of colleges. So there's a lot of R&D work done. We have a PhD student here in the office working on robustness and disproportionate collapse. So I think, yes, I think we've advanced quite a lot, but it's taken a considerable amount of time and effort.
Yeah, we can see that effort's been put in. I mean, and it's great to showcase, the work that you've done. I think it deserves it. Just a sort of couple of questions on high-rise. One is you mentioned that you have your own sort of section sizes. Are they normal hot rolled steel, or are they high-grade special hot rolled steel? No,
they're normal rolled steel sections. Just physical dimensions and thickness of materials would be unusual in the industry. Let's say we roll them to suit, as Shane said, we have very thick sections with a small plan area to try and minimize the impact on your net lettable space, your room space, and your occupation, and try and keep the columns as slim as possible and slender as possible towards the lower levels of the building.
Okay, thank you. And then I think one for you, Shane, on the cores. Obviously, the cores are incredibly important in terms of not just the design, but for construction. Do they tend to be slightly larger than on modular buildings to allow for the fact that you're not sort of modelling the modules themselves in terms of stiffness, and then B, the fact that you do have to freestand them? Do you have to scheme them sort of slightly different?
Yeah, they generally are a bit, not massive, maybe 20% increase in it, but in the external wall thickness. So it's not just, it's the stiffness we need, because we've obviously lost any external stiffness at ULS, but it's also potentially the modular connections are cast into the core as well. And for tolerance, they're generally recessed into the core. We can't use flush plates on the core wall, because there's no space to actually install them if the module ends up tight against the core. So we have to allow for all those recesses. All those things have to be allowed for, and as well, stepping the core is difficult or not really possible either, because in most buildings you can't step as you go up, but the modular connection, the modules obviously have to vertically stack. So if that eccentricity can only go so far, so we generally difficult to step the core walls as well. So that kind of adds to the concrete volume. But
okay.
It's benefit. We need the volume, the mass anyway, at the bottom of the core for the tensile forces.
Staying on course, we have a few questions on stability, as you'd expect with such a high-rise building. Are there any key differences in the stability checks for modular overturning? Do you consider potentially post-tensioning the core, because you don't have the weight within them? Is there been much modular construction in seismic zones, do we know, and are there additional requirements there?
So the first question was, the different checks we do. I suppose, like I said, the main additional check is the local buckling of the external core walls. If you have a big stair opening or a big riser, in a traditional building, you can just rely on the slab, the other side of the riser, to resist a lateral buckling, but we would ignore that. And just design the horizontal reinforcement. So you would have potentially locally some additional horizontal reinforcement. What was the second question before the seismic?
Yes, I mean, are you aware of high-rise modular in seismic zones, and are there any additional sort of checks that you need to do?
We're aware of medium rise in seismic zones, and not specifically high rise. Obviously, you do have your overstrength factors and to consider, but it's not. It definitely, especially in a high seismic zone, I think it would impact obviously your forces and your connections. So you'd have to have an overstrength factor on each modular connection and to the core, which increases your local forces and everything. So it would have an impact, but it's not something we've looked at in detail, apart from stuff up to 5 stories, which it actually doesn't have a massive impact up to 5 stories, but it's not something we've looked at for 20 stories and above.
Great, thank you. You had a really interesting slide in there on sustainability. Is that becoming more of a driver now in modular construction? Are we seeing a large reduction in embodied carbon, and that potentially being another benefit of the system?
I think we are. Yes, there's definitely huge benefits from using offsite construction in general, but definitely volumetric modular. And there's significant reductions, and I think all the benefits from waste, from what's going on in the factory in terms of material usage and efficiencies and high quality. I think there's a lot to be said for volumetric modular. I think it will become more and more popular. I think we just have to see how it progresses. It's suitable for some types of buildings, not suitable for all. So it won't take over, that's for sure.
We've got a whole series of questions on modelling, and I'm going to see if I can put these together. I'm fascinated by how you combine sort of the models. You have 2 engineers sort of working together, which is sort of a great piece of collaboration. But you mentioned ETABS and Tekla, presumably the geometric modelling is done in Revit. How do you share all of that information? That must be an exercise in itself.
It sure is. But I think Shane works with a different system, and I think there's benefits. I think modeling the building with 2 systems is generally a good idea. So the information isn't immediately transferable from one to the other, but having 2 systems means that we both model the same building slightly differently, and then we get to see if we're getting similar results with different models, which hugely beneficial, really.
Yeah. So I mean, Michael needs certain information from us, especially in like your even from your Plaxis model, your foundation settlement. So obviously that impacts because Michael's columns are obviously designed to the actual load. That even a change in settlement one into the building can distribute his loads. So there's a few iterations between the models in terms of the foundation stiffness and as well what cracking we have in the core, like what lintel beams we crack, what walls are cracked. Especially when you have two cores tied together, obviously the stiffness of that needs to be accurately assessed to get the forces between them. So it's just a few iterations of the models so you get something that matches.
And we have some sort of fairly detailed queries on stability modelling. How were the masses and stiffness of the modules modelled in that stability analysis, in the dynamic analysis?
So in our model, we'd model the diaphragm of the modules just as a 150 mil thick slab, like an RC finite element slab, but we'd reduce the stiffness just to account for some reduction in stiffness. And then the loads and the weight, we just apply a surface load then for the weight of we model the actual load bearing columns are modeled correctly. So whatever size Michael sends us in terms of the vertical column is modeled at the end. At the beginning, we estimate sizes, but they're all pinned anyway, so it doesn't really matter to the overall stiffness, but it's, we model the actual columns, 150 mil thick slab, and then we just apply a superimposed dead load to make up for the weight of the internal steelwork and non-load bearing steelwork and seating trusses. That's just so we get the correct mass at each level and your facade. It's relatively straightforward once you know the exact weights.
Relatively straightforward. There speaks the voice of experience, I think. And we've got a couple of really detailed questions now. I was fascinated to hear about the differential movement effects and how you can shed load from the sort of core to the modules. And we have a question of how you actually model that, that frictional effect.
No, there's no friction. So we assume it's fully free to slide vertically. So we'd have in our model, you'd connect, we model so that's another thing, when we model the modular slabs, there's a physical gap between that and the core. So they're not meshed to the core. And then we in terms of where Michael would set out his connections, or we coordinate where we actually put these connections to the core, but we model them in as one-dimensional line elements. And then they're fully fixed. So the connection that Vision have developed gives you full moment capacity and shear capacity on plan, but it does allow vertically sliding. So it's fully free. So it's just a fully free vertically sliding joint, but fixed in all other directions to the core.
Great. Thank you. It's like bridge construction, isn't it? I mean, you have to model the stage construction.
The actual movements, yeah.
And getting on to that, could you elaborate on the sequence of module installation? Presumably, do you need to know the sequence that you're going to install the modules to get all the connections from it?
Yeah. I don't know, Mike, so I can go first. So when we're doing the core, so obviously the core is built, say, a few months before the modules come to site. So as each level of the core goes up, obviously there's some, the core begins to shrink straight away. So say at level 10, you install a cast-in plate, but that plate is going to be shrink down due to axial shortening as the load is applied above, and also shrinkage of the core over time. So we need to work out at what stage is that plate installed on the building, and how far will it shrink by the time the module comes in at that level. And then we have to make sure it has enough tolerance left over as the module is finished, that there's enough sliding capacity in the joint. So that's why you have the stage analysis, so you can work out the level of the plate as it's installed on site in the slip form, the level of the plate as the module at that level is installed, and the level of the plate and module at the end. And then how much you have 30 years time, what level is the plate when you have the full shrinkage gone out of the core.
Okay.
So we'd issue a full specification to the contractor with all casting levels and installation levels, and they're all different from what's on the architect drawing in terms of datum levels, so there's a full separate specification for each individual line of plates. At each level has a different installation level. It's not relative to datum, it's relative to the time in the construction program that they're installed.
Okay,
that makes sense.
Yeah, that does, thank you. And we've got a few questions on design life. I assume that the modular buildings, they're designed for the sort of the normal sort of lifespan of a building. But also, are there any considerations given to sort of advanced considerations to possibly modifying buildings and how you would disassemble them or repair them?
Sure. I think with residential buildings, a lot of the residential buildings are very unlikely to have a change of use. So I think there's efficiencies to be gained in designing slabs to suit the widths of the rooms and the structure that's available at the time. So I think we definitely utilize that. With a corner post system, really the structure of the building is a minimum number of columns spaced at maximum 4.5 meters apart, I think, in the width of the modules. So you could open up a floor if you wanted to and fire protect the columns maybe slightly differently. And the buildings, I think, they can be reused, they can be relocated. You can reverse the system of construction that you use to put them in place to take them back down. I imagine, generally speaking, with modular construction, if you've got rectangular modules, you could see them being used somewhere else. But if, as in some of the buildings we've done, the modules are unusual shapes to try and fit an unusual site, then relocating them somewhere else and putting them back as a different jigsaw could be quite tricky.
Great, thank you. We've got sort of two sort of questions probably end on. One of them, or the key question, how high do you think modular can go? What do you think the limit is? I mean, 50 stories is, you know, absolutely astounding. How high do you think we can go? What's the next limit?
Yes, I can tell you a quick short story. John Fleming came to us in about 2008 and asked us to research what the highest modular building we could achieve was. I think we'd done 11 stories at that point, and we spent, I don't know, 6 or 8 weeks researching and doing a good bit of work on this, and came back to John and said that 16 stories, that's it. You're not going higher than 16 stories. And about 2 months later, John Kempton was with a 25-story building, which was completed in 2009 in Wolverhampton. So I think it'd be a little bit arrogant of us to say what the top level of a building will be, or what the highest will be. I mean, even now we've done, say, 50 stories, but you could probably go a little bit higher with exactly the same system, depending on the type of use of the building. If it was student accommodation, all the rooms were narrow, the exact same structure would go a good bit higher. I think the conclusion to this could come down to the structural system of the core and the issues related to horizontal dynamic movements rather than the limitations provided by the modular structures themselves.
Yeah, I think what we're beginning to look at now is, or I think personally, to go we could probably go maybe 10 stories higher, but higher than that becomes inefficient with the volume of concrete you need in the core. So I think we'd have to look at post-tensioning or some form of outriggers that you may have to go into relying on the modules as part of the stability system or some fashion, you know, to get it to work. I think the exact system we have right now has certain limitations, but there's just obviously unlimited options to keep going up. But it is, the core, the global stability is the main driver. Not the modules are, I presume, like just a vertical low path that just goes up forever. So it's the horizontal forces. Yeah.